So today we'll continue our discussion on the IoT enabling technologies, and we are currently talking about the different hardware components that are used to build an IoT ecosystem. So in the last class, we saw the basic components that are used to design the IoT, any IoT system. And when we say component, we are actually referring to the hardware component. So we discussed about sensors. We discussed how sensors need to be connected, or what is to be done after the sensor collects the data. So in that, what we found is it's all about data transfer from one component to the other. So if you look at the IoT design, and if you express that as a layered structure, you find sitting at the bottom is the device or thing that collects data, and then that gets transferred to other devices which lie on the upper layers of the IoT design. And these devices are also responsible for either translating the data or doing some processing on the data. So it's all about data movement from one device to the other, or from one infrastructure to the other. Now, in between, as the data moves, we discuss about what kind of devices currently are working on the data. I mean, what are the devices that are used at every layer, and what are the different ways in which this data is transferred. So what we talk about as components of IoT is the different devices in these lower and upper layers, and at the same time different networking techniques or networking rules, protocols that are used for transfer of data from one device to the other. So if you are talking about sensors, which are, or rather the sensing units that are collecting the data, they collect the data in some particular form, but that form is not, that cannot be used to process or make some informed decision. So the data that is collected by the lower layer is a very raw data that has to be processed, and it has to be stored in a specific way so that the upper layers can work with them and can extract some meaningful information. And that has to be, for that to happen, because there are two different devices residing at two different places, there has to be some kind of communication. There can be a direct communication between the device to a more sophisticated infrastructure called cloud, or there can be intermediate devices through which it has to pass. So whenever we talk about interconnection, we need to understand how the data will be transferred. So we discuss about protocols. So we understood that there is basically data movement, data processing, and in order to do that, we have to understand what are the devices that are working on the data, what are their structure, their limitation, and accordingly we have to understand what kind of data they are storing. We discussed about the basic component that helps us in actually capturing the data. So these are the devices that interact with the physical world and capture data, and we call them as sensors. They're very similar to how we humans interpret or collect data, how we make decisions. So we also have sensory organs, eyes, nose, ears, through which we interact with the physical world. We collect data in different formats, either a visual, auditory, or sense, touch. So we collect data in different formats, and every sensory organ is doing its own job. And the data that gets collected is finally transferred via these neurons to the brain, which processes the data and takes some informed decision. So a very similar model is also followed here, where we have different kinds of sensors that we use for different purposes, for capturing the physical state, for monitoring machines, for even monitoring humans. So we did all that. And then we tried to understand the operation of these sensors. What are they? They're basically units that collect record some physical state or collect some physical data and convert them into an equivalent electrical value, that can be some electrical quantity. But the reason why it is done is because the data has to be processed by a processing unit, which is something called a computer or some kind of a computing unit. And the computing unit understands data in the form of digital signals. So until and unless we collect the data and convert that into an electrical signal, we cannot provide that data for computation purpose. So we need to have some kind of mechanism through which the data will be collected and converted into a form that can be understood and interpreted by a computing unit. And sensors are basically these, which work on a particular physical principle, and this physical information or physical data that is collected is converted to an equivalent electrical quantity. For example, we saw different kinds of sensors, and we also saw how they are fabricated. The size of these sensors have basically reduced because of their sophisticated fabrication technology, and thanks to the advancement in VLSI technology that has led to sophisticated ways of fabricating these devices. So there are primarily two enabling technologies through which sensors are fabricated. One is semiconductor based, where the entire thing is a semiconductor device. And it follows Moore's law that gradually, as the size of the transistors keep on reducing, more and more uh, transistors can be packed onto a semiconductor die, and the size of the sensors have come down. We also saw the other technology that has allowed mechanical and electromechanical parts to be fabricated within this semiconductor die, and that has led to something called the micro electromechanical technology, and due to which we are now able to put rotating parts, mechanical parts, and so you can actually fabricate motors and gyroscope and accelerometer. And because of this, these sensors are used in many applications. For example, to measure the motion, to measure the tilt, rotation. So, and these sensors which are measuring all this are of a very small form factor, very small size. So that has actually led to development of this. This is one of the reasons why this IoT has found so much of usage. One of the reasons is these key things which are called sensors have become miniature, and they can be used in multiple applications, very cheap. That is one of the reasons why popularity of because due to the popularity of this IoT, the IoT system design. Okay, so we also saw some examples of uh, MEMS sensors. One of them was the pressure sensor that we discussed. We understood about the sensor that captures the idea of motion, which is called the accelerometer. We also have the one that measures the angular motion or angular displacement. We call them gyroscope. And together they form something called the IMU. And this inertial measurement unit, which actually has which measures the acceleration along the X, Y, and Z axis, as well as the rotational motion. So together they form 6 degrees of freedom, and accordingly, that entire thing is now available as a fabricated chip with different uh, degrees of freedom. For example, we have a 6-axis IMU, or we can have 9-axis IMU that allows magnetometer as well. So these are ready-made chips which are available now, and which can be simply used in any design that you can think of. Okay, so we also come across some common sensors for different purposes. And these, however, the problem that we discussed is that the sensors, they're not pure, that in a sense that sensors always have some problem, and these problems can happen due to imperfection in these sensors. And if you have an imperfection when you are building something, it may result in some errors. So you don't want to do that. And these imperfections or errors in these sensors are more severe if you take low cost sensors, because these sensors are designed using fabrication technology that does not that uses instruments or that uses processes which do not care about the accuracy too much. So there is a chance that the value can be an erroneous, not I would not say erroneous, but kind of a deviated from the actual value. So people, what they do is they make use of some model where you have some relation between the physical quantity and electrical quantity and the value that they obtain from the sensor. They fuse the two to get the perfect model or the perfect estimation. In some cases, we also require multiple arrays, multiple sensors. So they call them sensor arrays for different purposes. They have their advantages that they can average out the noise or isolate faults. Okay, and we also saw that it's one of the reasons why sensors have imperfection is because they go through a number of manufacturing process where there can be possibility of deviation. So it's important that sensors should be calibrated before they are used, because if you are using sensor for a particular purpose and that is uh, that needs a high accuracy of high accurate calculation, then you need to ensure that the sensor always gives you correct results. But that does not happen because in many cases, over due to prolonged use, the sensors start deviating from its actual value, or in some cases there is some mechanical damage due to which the sensor does not work properly. uh, some imperfect zero referencing was done. So all these can be factors that cause the sensor to give incorrect results, so due to which one has to calibrate them, and the calibration is nothing but finding out what is the actual result, finding out what the sensor is delivering, and accordingly adjusting the value given by the sensor. So for that, you need to have some reference. You find out what is the reference value or the golden value, find out what is the value delivered or provided by the sensor, and accordingly we make some additions or subtractions from the value generated by the sensor. And we have a formula for providing that. So the result that we have is called, let's say, the calibrated result. This is the one that is measured by the sensor. And these are the two factors that are used for adjustment. K is called the gain. So if let's say there's some uh, some factor times it's reduced, so you multiply that by the value, and then you add some offset to that. That's called the bias. So in this way, you try to calibrate the value that is obtained from a sensor. You also saw different kinds of sensors. Sensors are of two types, analog and digital. In some cases, the value that the electrical signal that is generated by the sensor is analog, and we know an idea of analog. So analog signal is nothing but a current or a voltage function of time which is continuous over time. So that is called analog. However, the other factor can be where you have the current or a voltage which is available only in two levels. So this is called the digital signal, right? So sensors can be either analog or digital depending on what kind of an electrical quantity or how they deliver the electrical quantity with respect to time. Is it a continuous value or is it only a discrete value or only between two values? Now, the reason why this has to be understood is because when you are going to use these sensors, you have to understand how are you getting the data. Say, for example, if you are getting a data from a digital sensor, you already have the value in the form of a digital signal. It's like a pattern of zeros and ones. If I call one as the high logic level and zero as the low logic level, so it's already a pattern of zeros and ones. So you can directly feed that to a microcontroller. Okay, so that is possible. But in case it is this signal, which is a continuous signal of variable range, then you need to do some additional processing before you can generate that. So there is some processing to be done so that then you can arrive at this and then you can feed it to the microcontroller. So this additional circuitry which has to be there is the overhead for an analog sensor. So what we do is we convert this into a discrete signal, then we round it off, and then we finally encode. So if it is something of this, you first The first step is we, instead of taking all values, we take only certain values. Okay, we take certain values. So if we call this as the analog, this is the one that is actually generated. This is called discrete. How do you discretize that? Well, you don't take all values, you take only certain values. And way to do generate from here to here is called sampling. That you take samples, right? Only the certain values. So here we have a sample circuit. It's called sample and hold. It's like a gate that allows the value to be passed for some time. I have drawn here to be those, but it actually is. So if I can draw it. So the sample value would be something like, maybe here you take this as a sample. Then from here onwards, you take this as a sample. You can take from here, let's say this as a sample. So this is how you can generate samples, and then you can generate this discrete waveform, right? I mean, this discrete signal. Now, this can be, what we can do is we can take the range of this. Okay, so that is lying between from, let's say, from some plus V to minus V. So plus V to minus V. And then you can round it off. They can divide this range into number of sub ranges, and accordingly you can round off this particular sample value to its nearest integer value. So if this is, let's say, 2.4, the nearest value of this can be rounded off to 3. If this is, let's say, 4.6, this can be rounded off to 5. And these are nothing but one of the values within this range. So once you get these as rounded off values to the nearest integer, you can very well encode that in the form of a binary. And that can always be translated into this digital signal. So this is the basic idea, that you have analog signal, you sample that to contain a discrete signal. From discrete, you obtain these values. So it's like if this was, say, 3.5, now you reduce it to a value of 3. So it's like this that you have. How this is called quantization. Okay, so next thing is you apply quantization, where you round off to the nearest integer level. Then once you obtain that, then you use encoding, where you convert that entire thing into the binary representation. So this is the additional thing that we did in case of analog sensors. Okay, so what we said is that, well, it's not enough that you get the data. Now, once the sensor is getting the data, it's continuously capturing the data. Now we have to store it somewhere, right? Because the idea is that the data that is obtained from the sensor will be processed by some computing unit. But the computing unit, until you store the data, will not be able to work on that. So then there has to be some kind of a storage. And that is the reason why we say that, well, this sensing unit that you have that captures the data, okay, and this data is, I assume that there is an analog to digital conversion, that the data was analog and here you get the digital data. Now this data has to be stored in some kind of a storage, which we call memory, but that cannot be possible directly. It will be sent to the CPU or the processing unit, which in turn will send it to the memory. Okay, so this is how the process happens. And so overall, if we uh, you know if we group all these together, we call that as a sensor node. So you have a sensing unit, you have an analog to digital converter, you have a computing unit, and memory that stores the data together. Along with that, obviously, because all these are electrical components, they need to be powered up, and for that we need to have some kind of a power source. And usually these are semiconductor components, so they are low voltage operated devices, which normally has to be battery operated. We don't prefer AC main supply for these, so they are low voltage devices. Okay. Now we can go one step ahead, and we can also have everything into one single unit, and that's what we call the smart sensor. So the sensing unit, the computing unit, the storage, the A to D conversion, etc., In some cases, some kind of processing also has to be done right at the sensor, whether you're going to take some data or not, or you're going to represent a data in a particular format. So some basic kind of algorithms also need to be worked upon. So you need to have some kind of a logic circuitry that will be associated with that. So all these together is often called a smart sensor. Smart sensor because there is some kind of processing that can be done and some kind of a decision making you can take. So you can run some algorithms here. That is the reason why it's called a smart sensor. We'll talk about that later on. And this is overall the sensor data acquisition system for an IoT based system, where we have, as you see, physical phenomena giving you the data. The data is captured by the sensor. There's some kind of a signal conditioning. Conditioning means either you want to remove some noise or you want to convert that into some kind of a form that is understood, as in case of A to D conversion, etc. And then we have this part where you either do some kind of an intelligent, some data storage, pass it on to a computer to do some kind of an analysis, or the output which is generated via this computer is via this actuation or acquisition hardware is used to control some other device called actuator. It can be this way as well. Okay, so this is overall the picture of the IoT system, and this part is what we call the cyber physical system, the CPS, right? Where we have some device that captures the data and some device that is controlled by the result generated on the data which was captured. The data was captured, it was processed by some computer, and some results or decision making was there which was used to control some other device. Okay, so physical things are actually controlled by cyber world. That's why it's called cyber physical system. Now here we can add some, this connection between the physical world and to the cyber world, where you actually perform the decision making. If it is through an internet, that's what is an IoT. So this is a digital sensor circuit that we see has a sensing unit, which is a humidity sensor. We have a temperature sensor. So these are the units that are capturing the data, and they are sending it to a control logic. Now look at this. This particular chip has both humidity and sensor. So it's important, but however, they are sending it to a controller. So what data you need to send has to be decided here, whether you are going to send the humidity sensor, humidity data, or the temperature data. So this control logic will decide on that. And this particular chip is going to interface with a microcontroller, which is the computing unit that is going to record the data, store the data, as well as process the data. But these two have to be connected, right? So this 7005 has to be connected to some microcontroller. So there has to be some kind of an interfacing. Okay. Now this interfacing that you have to do will be through some wires. And as you will see later on, that these different chips that are going to be connected to the controller, they send the data in a particular way. So this interface that we are going to talk about, okay, has to be understood. And this is the first communication that you should understand it happens for an IoT system. The connection that is established between the sensor and the microcontroller. That's the first and the lowest level communication that takes place. This is a near communication because the communication happens between two devices which are very near. And it usually happens through a wired communication. So the interface where the sensing circuit has to send the data to the microcontroller will make use of some interface. We'll talk about the interface just now. Here, as you see, there is an interface that is used, which is called I2c or I2c. That is an interface that is used. So when you are connecting your sensor to any development board or any microcontroller, you have to know what kind of interface is supported by this particular device, and whether your microcontroller has that interface. I repeat, when you are going to connect a sensor or a sensing circuit to a microcontroller, say for example, you want to use some sensor, let's say a sonar sensor that measures the distance of an object with a Raspberry Pi, you have to find out the interfaces supported by this and whether this particular Raspberry Pi also allows the same interface. If this does not support the interface provided by a particular chip, then you cannot use it in that. Either you have to go for a different sonar sensor chip, or you have to take a different variant of this microcontroller which supports it. Maybe Raspberry Pi won't work, you go for some other microcontroller. But this is a costly step because normally we don't prefer changing the microcontroller. We prefer changing the sensor depending on what kind of interface it is sending. Say for example, SI7005, this chip you take for recording the humidity and sensor for temperature. And you see that it is having an I2c or I2c protocol for communication with the microcontroller. You should know what is this particular protocol, number one, and whether the microcontroller that you are going to use has an I2c. Raspberry Pi actually supports I2c protocol. We'll talk about that in just a moment. So it's fine. You can take this sensor circuit, you can take Raspberry Pi because Raspberry Pi supports I2c. I2c is a serial protocol. The data that is transmitted from the sensor which captures it to the microcontroller is serial. Let's say, for example, if assume that this is a digital sensor. So the data it will capture is like 101010. So this is the 8-bit data that has to be transferred. Now, if it is transferred one by one, like this is first, then this, then this, then this. So it's a serial way of transmitting. Okay. I2c is one such protocol where you have a clock and you have a data. Only 2 pins through which it starts transferring. So there's a start to clock kind of a thing that begins or mentions that, okay, now I'm going to send the data. So it's an initiation and then the data is sent and then there's a stop. It's pretty simple logic. It's a very easy way of communication. Okay, we'll talk about that. So you have to keep in mind whether this sensor is allowing you or not. We already have mentioned about that if you are going to use it for an IoT based system, you have to understand that whether the sensor, we have to understand the sensor, what kind of a sensor have you interfaced to your computing unit. And as we told that many a times, you also have to work with analog sensors. So in that case, the data that you will be generating will be generated at a particular rate. Okay, I mean the analog sensor may not give you the will not give you the digital data. So you have to add some additional circuitry which is going to generate the digital data from the analog. Now the data that is going to be generated will be generated at a particular rate, and the rate will be decided by the sampling rate. How frequently you are taking samples from the analog, right? Why? Because whenever you have some value like this and you sample it, you may sample it at a different rate. You may sample it in this way, or you may sample it very, very close, depending on. So depending on the sampling rate, you will get those many samples. And the important thing to understand is when you will be feeding these to microcontroller, the microcontroller will be processing on each sample, each one of them individually. Each is a data. They have to be stored, they have to be processed. Now, if you use it for a real-time system where you are going to process one data at a time, that means that when you are finishing the processing of data number A, your data number B is ready. So you should understand that the computing unit should be very fast enough to complete the processing of data number A before data B arrives. Because if it does not happen, then you lose data B. You should understand that. Which means that the processing unit should work at a rate at which the data is provided to it. This is called the data rate, the data access rate, the rate at which the data is accessed. It should finish off. Now, if you try to increase the data rate too high, which is beyond the capacity of your CPU, then you lose a lot of data. Okay. At the same time, if you are sending the data at a very fast, at a very slow rate, it is taking a lot of time, and by the time it is remaining idle. Majority of times it is remaining idle. So it is unutilized. So there should be a balance between the rate at which the data is captured and sent to the CPU. It's very, very important to consider that. Okay. Now, if you use more samples, it is better. The more samples you use, the more frequent samples you use, it's better. But the problem is that there's a capacity at which this particular thing can work at a particular rate, but they may not be able to work at that same rate. Okay. So when you deal with real-time data and when we use IoT sensor nodes, majority of the times we'll be dealing with real-time data because there's a communication involved, right? So this sensor data will be sending data to some cloud, or you will be doing some processing at some remote place. So there is a time that will be spent in sending the data, and then we'll be processing. So you should understand the rate at which these devices work, because if there's a rate mismatch, you are not working with the full potential of these devices. Okay, so sampling rate decides the data rate. Data rate decides the real-time processing rate of your microcontroller. And that, in fact, decides the output rate. So still working with streaming data, it's still a challenge rather than working with a static data, because the rate at which you have to work has to be pretty fast. You have to support the communication methodology, the communication techniques, protocols have to support all that. So there are a lot of things to consider when you are talking about an IoT-based system. Say, for example, this one. The camera is a sensing unit which has a processor inside that captures the data, which is an image. And this entire image is captured at a particular rate. You're filming something, right? And then that has to be processed here and generated as a display. That's a real-time data processing. But the rate at which this is providing you, if your processor is not working at that rate, you will see a lag. So you have to understand the rate of sampling, which is governed by the A to D conversion rate. So the faster we can generate the analog to digital converters, the better. But there's a limit currently to the rate at which you can work with. That is the reason why we have to understand what is the maximum rate of the A to D converter that you are working. That will be governing your data access rate. Okay. So that was what we covered, and we understood that this is overall the picture that we have got so far. Now, if we can, formalize that, what exactly we got as an understanding of the sensor node, we see that there are basically 4 components in that. One, which is sitting right at the bottom or at the most innermost part of this node, that is responsible for connecting to the physical world and capturing the data. We call that the sensing element, the actual physical process that is involved. Now, along with that, we need some kind of a sensing circuit, okay, which is surrounding that or enveloping that, which is basically for excitation and amplification. You convert that into kind of an electrical signal, be it whatever it is, analog, digital, doesn't matter, but there is some kind of an electrical signal. So this is a physical property, which is the physical device, let's say the pressure sensor. So the capacitance that you create here, the device that you build is this element. And now you bring in the electrical property in that. You exploit the electrical property through the sensing circuit. So you have some kind of a electrical property that gets created. These two is what makes up the sensor. Now then we have the digital compatibility, whether you are making it, the data generated out of that, whether you are making it suitable for storage in some digital system, such as a computer. And for that, you need to have some kind of an analog to digital converter. and you need to understand the interfaces that connect the two, the computer or the microcontroller and the sensor. That is why we are calling it digital compatibility. So what we talk about here is we talk about the A to D conversion, converting that into digital signals, and second, how do you transfer that? We talk about the interface, what kind of an connection you are using to connect the sensing element with the microcontroller. Finally, you have the IoT system compatibility sitting right at the periphery. So it's like here you talk about, well, am I going to keep the computation along with the sensor, or am I going to keep the computing unit as a separate unit? If it is going to be separate unit, then I have to link the two. If I have to link the two, that means what kind I have to send the data. There will be some communication involved. What kind of a communication I'm going to use? Okay. What kind of a computation will that processing unit do? Will it run simple algorithms, or will it be only simple storage, or will it have some kind of an sophisticated algorithm that can perform some decision making? How am I going to power that particular device? Will it be a battery operated? Will it be a wired communication or wireless communication? So that involves once you come out of the sensing element and the sensor chip, whether you want to keep it or you want to allow it as a separate unit. This is basically a sensor node. Okay, we have quite a few sensor nodes at our lab. We have three kind of sensor nodes. We have a complete IoT lab setup, which was designed and provided by CTAC Bangalore, and we have three kind of sensor nodes available at our systems lab at IIIT. And we call them, we'll talk about that later on. We have three kinds of nodes, sensor nodes available to us, which is one is that uses Bluetooth technology for communication. The other uses a Wi-Fi methodology for communication. And the third one is a low power. So we have three kind of such sensor nodes available with us, 15 of them each. And we use them for data communication between a aggregator, or what we call the gateway. So we call them the Bluetooth modes, okay, the Wi-Fi modes and the low power modes, the BLE modes. So this is, we have them. Well, so as you know that now that we have sensor nodes, understanding of sensor nodes, we can connect these nodes to build a network of sensors. So assume that your sensors are smart. Smart means they have the sensing element, they have the additional circuitry of A to D conversion, the interfaces, and we have the computing unit along with that, which can perform some very basic computations, run some very simple algorithms. So that's an entire node, you call it. You're not just calling it sensor, you're calling it sensor node. Okay. So if you have these sensors, or we call it the sensor node, as you see here, there's a sensor node, right? Many sensor nodes. Now, what you do is you connect them to form a network. And these sensor nodes are connected wirelessly. As I told you that we have here different kind of modes or nodes available with us, which connect through different wireless protocols. It can be Bluetooth, it can be wireless, low power and low range, obviously, but we can connect these, they can communicate. Now, what happens is, as we are talking about sensor nodes, and the nodes have the capability of computation, data compaction, means you can reduce the data size, aggregation, and analysis. So they are not merely physical devices that only capture data. There's more than that. They have the capability of computing some, or they run some basic algorithms. Okay, they can perform some analysis and can also communicate. So they have the communicating facility. These are called wireless nodes. And each node has an independent computing power and capability to send and receive responses, data forward, and routing capabilities. That is the reason why we today have we see huge popularity of these kind of systems, where it's not just restricted to data collection. You have a computing power given to that, and you deploy that at different places. These nodes, they communicate the data, and together they may solve a particular problem. Okay, so this network of these nodes, these smart nodes, is what we call wireless sensor network. So each node that you see here is a sensor node, and they communicate among themselves. They interchange or they exchange data for completing some kind of a task. Okay, now there are different ways in which you can work. You may have, okay, there are many nodes, but one of them you make as a master node that collects the data, sends it to the cloud, gets the, because these nodes also have a limitation in their computation power. So for high order storage or for permanent storage, let's say, you may make use of some third party infrastructure such as cloud. So one of them will be aggregating that and sending it or recording that for backup, or maybe doing some additional analytics here. And these nodes also are capable of doing computation. Okay, so it can work in this way. So this is the idea behind developing something called wireless sensor network. So today we are talking about self-driving cars, unmanned vehicles, even drones. So you can consider them to be nothing but wireless sensor networks, where we have, let's say, a swarm of robots or a swarm of drones that are going to do some particular task. Let's say some aerial surveillance in some uh, enemy territory. So you're going to send some, let's say, 10 drones, and all of them will be service will be doing their surveillance in a limited area. Well, but then overall they have to aggregate the entire terrain and send the information back to the command center, right? So they are like, okay, I am moving in this particular path, you don't cross this limit. So they have to communicate. So in this way, there will be these sensor networks that will be communicating and will finally aggregate the data and send it. So that's a typical example of a wireless sensor network where you need to. It's a very, there are some challenges involved here. How are you going to power these individual units? How long will that sustain? How will they communicate? What kind of, because these are low power devices, so they cannot communicate for long. They have to be powered up, and you have to use a protocol that will only allow low range communication. Because if you go for some protocols, it may require more power, which is not possible by a battery operated device. So there are a lot of challenges and opportunities for research in this. Okay, then we come to the device, which is actually the one that will be controlled, and it's called actuator. So our ultimate aim of an IoT system is to make some informed decision. And one of the informed decision would be to control some physical device. Majority of the times, these physical devices are some kind of rotating devices like motors or vibrators. Okay, so we call them actuators. What are they? They are devices that take the actions. Here is the other way around. You don't provide the data, but you get some command depending on some information that was, some analysis that was done, and the device is made to change its state. Now, how do you get this? Either you get a command in the form of a pulse, or there is some kind of a state change that is mentioned, something. So here the conversion is from electrical energy to physical action. Okay, this is the difference. There are different examples of that. For example, you see here in this diagram, there are different motors which have been shown. So this is basically the idea behind these are called the actuators. Now, one of the actuators that are very commonly used is called relay switch. What is that? This is an example that has been shown here. It's an electronic switch. Okay, so it's a switch. That means it has an on-off condition. So it's an electronic switch which can be controlled by a 1 or a 0 from the port pin of a microcontroller. Now, many a times you need to, use some kind of a switch on and switch off, circuit on and circuit off kind of thing that you want to do. So in that case, you prefer these, they're called relay switch. So what happens is, let's talk about the operation. It's a switch which makes mechanical contact when the input magnetizes, as you see here, right? So when you have this as the input and you have a magnetic coil here, this blue pink line that you see here. So when you have this magnetized, then when the input magnetizes, there's a pull involved in that. And when there's a pull, then you have a circuit getting closed. When the circuit gets closed, you have some kind of an output that you see in this green bar, the light that you see here. It's like a circuit getting closed when the input is magnetized. And when it is demagnetized, it releases that the switch, and then the circuit breaks and it is off. So it's like this. Now we can make use of a typical example of actuation is, as you see here, we have a sensor. Say for example, we want to build a detection mechanism, or you want to make an automatic sprinkler, okay, for your garden. So what you are going to do is you are deploying some sensor that is measuring some temperature, and you measure the temperature of the surrounding, and accordingly there's a control center that gets this information. That control center can be local, or you can have a direct sensor node, or you can have some kind of a server where the data is logged and the center sends it to a controller of a sprinkler, okay, and the sprinkler is again a motor. That's, let's say, it's when it is rotated, the water falls. When you turn on the relay switch, the water falls. When you turn off, the water, the tap is closed, or the sprinkler is closed. So you can think building systems in this way. Okay, right. So okay, so now let's talk about the concept called power management. So we saw that whether it is a sensor node, a wireless sensor network, all these are devices that are either semiconductor based, mechanical, so they need some power so that they can operate, right? And the power that we are talking about is two different types of power, power source that we have. Either you have an AC mains, or you have battery operated. Now, when we talk about power management that you are going to use for your IoT based systems, you should look at certain things. Number one, how much of a voltage do we require? How much of a power am I going to require? And that will be decided by the kind of components you will be using finally for your device. We will be talking about imperfections, whether your voltage will drop or be, whether it will remain constant. What is the power rating? Power rating means, okay, we have your voltage source, but is it delivering same amount of current, or the current coming up down? So we need to know that. Then what are the real life design challenges? How much efficient is the power source? How can you rely on that? Voltage regulator, whether it is constantly giving you a fixed voltage. This is some of the power management issues that has to be taken care of. Majority of the times we see that in case of low power electronic devices, or the handheld devices, the gadgets that you work with, they typically use connectors which are, or power source which are either batteries, or many today, they use the connector itself as a power source. The common connector that you have, which is called the universal serial bus, or USB, that itself behaves as a power source. Okay, so as we have seen here, many of you are aware of the this connector called USB. You have been using it day in and day out, at least for charging your mobile phones. That's a very common connector that we use. So what is it? It's actually a voltage source which is present inside. So USB port is commonly used for power today. It has a fixed voltage of 5 volt. As you see here, there's a voltage line. And there are two kind of current ratings. So it's either a 100 milliampere amount of current that can be delivered or 500 milliampere. So 5 volt into 100 milliampere. So 500 milliampere volt, okay, or milliwatt, or 2500 milliwatt. Now cell phone chargers are USB connectors. They are just physical connectors. Okay, there is no USB data transfer, and you have to understand that it's 5 volt. So this can only power up devices or circuits which work at a 5 volt supply. Thank God majority of the CMOS circuits are 5 volt operated. So a USB power source is good enough to provide the 5 volts line or supply to your entire power line of your electronic circuit. And once the electronic circuit power line or your board on which your electronic circuits or ICs have been fabricated, once it gets the 5 volt supply, now you can work with that. So 2 lines for data transfer and 1 line for the source for the power line. So this is a typical USB connector used. Okay, so power handling is a challenge, right? Because you have to have AC to DC conversion. Maybe you don't have a facility to. Now you know that electronic circuits are DC components, whereas your AC mains is an AC. So you need to have an AC to DC converter. You may require an adapter. You require maybe some kind of an SMPS, switch mode power supply, which accepts 220 volt and delivers 5 volt. So it lowers down, step down. So, but it's not only that you are happy with the lowering of voltage, you should also be concentrating on what amount of current is generated by that. It's called current rating. 3.3 volt is giving you 14 ampere. 5 volt is giving you 30 ampere. Plus 12 volt is giving you 20 ampere. Maybe this is working. You multiply these two and you get the power rating. That is something which is important. Okay. Here you have 150 watt. And here you have, let's say, 12 to 24, 240 watt. Okay. So maybe the wattage will be deciding how much of a current rating should you prefer. And for that, you'll have the what kind of SMPS should you take. Power consumption, well, this device really consumes power because so many of the devices are inside and it is drawing power. And the power should not drop. So when you are talking about the power management source, you should consider that the power should not drop from a certain voltage below that. Okay, so that is about it. There are a lot of sources that we have for providing power, and majority of them are batteries. We have quite a few batteries that we use for these low-end devices. Majority of them make use of something called lithium ion batteries. We'll be talking about that. It's a very, very popular, this devices, the battery also has to be thought of because the device that you are going to work with is a very small form factor device. It is of the order of, let's say, a coin. So how will you give the power source to that circuitry? Entire circuitry is sitting on a device which is of the order of, let's say, 1 centimeter radius. Now the problem is you have to power those circuit. What kind of battery are you going to use? What kind of power source? You cannot connect a main supply. So what kind of a battery would you prefer? So battery has also been a consideration when you talk about IoT. What kind of battery should we prefer? And majority of the times it was found that lithium ion or lithium poly, they are the most popular batteries that are used. They are portable, and because majority of the wearable devices are low-end devices, they have a very high energy density, they have a very low maintenance and ease of handling. So let's see structure of that. These are the lithium ion batteries that we normally use. It comes in different forms. It's either cylindrical, prismatic, or coin. So any of these three forms. Good enough voltage it provides, 3.7 volts. Battery capacity is milliamperes running to hours. And we have the charging current. Okay, very fast charging. So this is typically one of the reasons why these batteries are preferred. This is also something that has come up, and it's called flexible lithium-ion battery, and they are used for wearables. Why flexible? Because the gadgets that you work with, in case of for medical purposes or for wearables, they are having a structure which has to bend. So your battery also needs to be flexible so that it can fit into these kind of devices. Okay, one example that you see here is a lithium ion battery, which is a flexible one, which can be used for wearables. And this is a typical view of a flexible lithium ion battery that you see, which has been unpacked. Okay, and as you see here, these are the electrodes and this is the insulator. So it's not a metallic part that a metallic casing on which you normally find a battery. It's kind of a flexible material. We think about different kind of materials which can be treated, which can be molded, or which can be which can change their shape, and not change their shape in the sense that you can bend them. Okay, but you have to think about what kind of structures can we use to design batteries. So as you see here, one of them is shown. This is the lithium ion battery, which is flexible, the insulator and the two electrodes. Okay, so with this we have a basic idea about the different components and sensors, actuators, sensing units, battery, done. But the next thing to worry is, well, we got the data, right? We captured the data and we are getting that periodically from the sensor. What to do with that data? So the data that is provided by the sensors first has to be stored, then has to be processed and analyzed. And this is what we call computing, right? So we need to know what is the need for all this. So sensors, they convert the real world entities to electrical signals. The data, however, generated by the sensors are raw data, and we have to extract some information from them. So first you have to store, then you have to transport it to some computing unit, and then you have to sort the data, or you have to do some kind of a processing. And the processing is basically done to perform some informed decision making, because depending on the decision that we make, we would be either analyzing or rectifying ourselves or improving ourselves or triggering some other device. Overall, to make a better life. That is the basic idea of informed decisions. Okay, because we are generating data. So can we use some intelligence to make the decisions more better? Here you go. So when we talk about computation, we talk about so computation actually is distributed. Some computation happens at the device level, some computation happens at the cloud. Okay, so as you see, we have been so far discussing about this part. We were talking about the sensing element, the sensing circuit, the signal conditioning circuit, and finally storage onto some kind of computing unit that is very local. Okay, and the other side is, once the computation or the data that you generate is beyond the capacity of the local computing unit, beyond the storage of that, and you need to do more sophisticated analysis, very bulky algorithms. You want to run some, let's say you want to do some object detection algorithm, and you have to run some neural network models. That is not possible to run on a simple device such as a Raspberry Pi. you have to take help of more sophisticated infrastructure, and that is what we call cloud. Here is where you run all those high intensive algorithms, right? So this is another computation that happens far away. So if you look at the computation, one is a low level computation and the other is a high level computation. The low level computation is more about data acquisition, data storage, small kind of analysis. High level computation is more about analytics. So, but the problem today is that there is a communication that is involved between the low level device and the high level computing unit, and that is a wireless device. And these have their own limitations. They have their own challenges. Latency, security, right? Primarily latency. So when you are talking about devices that have to be working in the real-time environment, latency in this is a real challenge. So what we do is, the idea is to bring the computation as much as possible to the local side. It has to be a local node. Okay. Or you have to reduce the requirements of connectivity. This is the main idea, that we will do majority of the computation right at the IoT device. That's called edge computing. I don't know whether many of you had heard of this term, but this is what is today the idea. Edge computing, or as much as possible, majority of the computation done very close to the device which is capturing the data, so that the computing requirement has to be reduced, because lot of power is spent on computation, lot of time is taken in computation, or sorry, in communication. So you have to reduce the communication. You only keep this for backend or for high level information, this cloud, etc. And the data interface has to be simple. This is the overall picture today, right? Do you agree to this? Okay, so I stop here to take your questions if you have any. Well, so once we get an idea that computation is distributed, some computation happens at the local end, some computation happens at the cloud. And we have already seen different models of IoT design, or rather we should say different IoT level design. Okay, so if you see, if you just recap, we studied 6 different levels of IoT system design. In the first level, we had the node which was doing everything, right from data acquisition to storage to analysis, and there was no cloud computation involved in that. This was IoT level 1. In IoT level 2, we saw that the node, the sensor node, was only doing data acquisition, that is monitoring, and some preliminary analysis is being done. Okay. So, and the storage was done in the cloud. So look at the IoT level 2 difference. So the node was capturing, so the sensing circuit is there and performing analysis. The sensor node is also performing analysis. So that is the reason why the microcontroller which is attached to that sensing circuit, or the sensor node which has the microcontroller, is able to do some kind of a very basic analysis algorithm. But the storage, because data is generated huge, is done in the cloud. The cloud is only maintaining the storage, maybe the database. IoT level 3 is the one where the node is only doing monitoring, only capturing the data, no analysis even. The storage analysis was done in the cloud. This is level 3 design. Okay. And in level 4, we went one step ahead and found that we can have many such sensor nodes, multiple sensor nodes. Each one will be doing some data acquisition, as well as they will be doing them local analysis. And the storage will be done in the cloud. And the cloud will also perform some high level analysis. Okay. So the, working with the data and running some very sophisticated models, etc., will be done in the cloud. IIT level 5 was where you have these multiple nodes, but unlike in level 4, where each was directly communicating to the cloud and storing the data, here the storage will be, or the communication to the cloud will be through a coordinator node. That is what we call a gateway. This coordinator node, so the local nodes, the sensor nodes, they are only for monitoring purpose, for data acquisition, right? And out of that, one of them will be something called a gateway, which is the coordinator that actually sends the data to the cloud. And in the 6th level, which is a more sophisticated level, we had a centralized controller which was capturing the data. And here too, this is the one that will actually be responsible for coordination between the data, the monitoring node as well as the cloud. Okay. So this is what we have studied, and we saw that the design, and with this is I thought that let me give you the idea of how the distribution of computation happens when we come up with different levels of system design. Okay, so now we come to the computing unit, which is called the microcontroller. Now all of you must have taken a course on computer architecture, and you must have come across the term called microprocessor, whose basic idea is to execute instructions. If you remember, microprocessor is a device which is having some components, primarily 2 components, an arithmetic logic unit and a control unit. And what it does is it executes instructions. This is its primary job. It executes instructions. Now the instructions that it executes have to be provided to it. And the way to do it is that we use some kind of a storage called memory. We keep the instructions one by one written in the locations of the memory. And this microprocessor fetches them and executes them and gives you the output. This is how it works. Now these instructions are written in the language of the processor. They are either, they're written in the form of 0-1 pattern. They're called binary or executable. And they are made, the CPU or microprocessor reads them, executes them. Now, majority of the time, as you see here, you have a storage which is storing the instructions so that the CPU can fetch them, execute, and give you the result. And the results are also sent to some kind of an IO. Okay, this is how they do. And for that, they have buses like address bus to locate the location, get the data from there, and output bus to just send the data. So this is how things work. But you see, all the peripherals and everything is outside this chip. This is the typical microprocessor communication or microprocessor system. Now people thought that, well, why to keep this memory and all everything outside? Can I have a chip that will contain the memory? Can I have a chip that will contain the IO, etc.? And can I build one single block that will contain everything instead of having separate chips? Because that increases the size. Okay, then said, fine, that's what you called microcontroller. So people devised this. And there you see that in this single block, you have a computing unit, which is the microprocessor that executes instructions. The mechanism remains the same. There is a memory. It reads the instructions from the memory. And if it has to send something, it sends the output via the IO ports. But everything is inside, and they are the IO ports, the memory, the processing unit, that is the microprocessor unit. Everything is hosted in one single block. So obviously, the memory with which you are going to work will be a very low size memory. You cannot have a very large memory within this block because the block itself will have a capacity. Which is order? 1 MB maximum, maybe. This order of memory you allow. So microcontroller will only contain programs which will be of the order of, let's say, 1 MB. So what kind of applications do you think is suitable for microcontroller? Applications for whose code, whose executable size is low. The number of instructions are less. So for that applications, microcontroller is preferable. That is the reason why in IoT based systems, we are preferring microcontrollers and not microprocessors. Because the job that has to be done is a very simple job, like collecting the data, storing, running some basic algorithm. So for that, if you write a code, that will be very simple code and that will only take very limited amount of size that you can store within the memory available in the microcontroller. You don't need a separate adjacent memory for that. That is the reason why, and that will reduce the size. That is one of the reasons why microcontrollers are preferred, right? And as you see here, a microcontroller has a lot of other components as well, like timers, analog to digital converters, signal IO, serial IO, and other devices. They are supporting devices. Why? Because you will need a clock for running all this. That is why you need timers. You need timers for data communication because there will be some sensor chip which will be connecting it to via this to the microcontroller. So the connection has to be established and there will be data transferring at a particular rate. So there will be a synchronization that is needed. You need to have an A to D converter if this is an analog. So then this data will first be reaching here. From here it will be sent to this and then it will be sending to memory. So you need an A to D converter. So you see, you have a computing unit, microprocessor unit, memory, IO, and some additional supporting devices for different purposes. It's a very, very suitable thing to work to use while you are working with or you are planning for building an IoT based system where everything will be in a reduced form factor and you will have sizes which are minimal. Okay. It's a typical example of a very commonly used microcontroller, a very old one by Intel. It was called 8051. And there you see the different components that it has. It has a computing unit which is called the CPU that processes the instructions. It has a RAM which contains 128 bytes. Look, 128 bytes. It has a ROM, read-only memory, where you cannot write anything. You can only read the instructions from there. Usually this is used to keep instructions and this is for keeping the data. That is how they make this. This is also of 8K size. You have some timers and you have some other peripherals and the buses which are internally connected. So overall, this is one single chip. It has its own language, assembly language. That's all. So microcontroller is a reduced, say a reduced form factor computer where everything is housed in one block. Okay, now even we have extended that idea, and as I told you, VLSI design or VLSI technology has increased in leaps and bounds, and today we are able to actually put not only the microcontroller but all the peripherals and many microcontrollers together in one single chip. The peripherals, the microcontroller, the ports, everything in one single chip, and that is why it's called system on chip. So it's an integrated circuit that integrates multiple processes. That's the first interesting thing to understand. Not one microcontroller, but maybe 4. So I'll give you the example of one that I am currently working with. So as you see here, it's R Cortex A53. This is one of the microcontrollers. And you see there are, how many? You have ARM V8 32-bit CPU. This is there. Then you have a Neon SIMD engine with crypto extension. So this is also a collection of processors where you can run a cryptographic algorithm in that. So the architecture is designed to run some cryptographic algorithms. So you can extend that. I'll give you an example of a chip which is called Exynos. Okay, this is the chip that is used in majority of the Samsung Galaxy mobile phones. And what we have here is two kind of processors. One is called the big processors and the other one is called little processors. Okay, they are four in number. There are four processors inside, and here also there are four processors. Now they are low power processors and these are high performing processors. That means if you want to run some high performance algorithm, these are made use of. When you want to have a low power algorithm, they are used. Look, and everything is one single chip. So there are total 8 processors inside, 8 microcontrollers. This is what we are talking about. Multiple processors. Other hardware units are there. Say for example, as you see here, there's a cache memory which is there with parity, with ECC module, that is the error checking facility. We have some kind of a bus interface, debug and trace multi-core. So hardware units are there. We also have some embedded software. Software is also present inside. You don't have to, write. So you have a chip on which you already put your libraries and operating system, etc. This is a typical block diagram of a system on chip. As you see here, you have, this is a bus. This is an ARM processor, for example. This is, you have a voltage regulator that ensures that the voltage always is of a certain value. And then this is the system controller, the different ports, etc. And one example of that is this ARM Cortex A53, which is present in the commonly used prototype platform, which is the Raspberry Pi board. So Raspberry Pi is a very common computing unit that is used. And this board has a chip, as you can see here in the red figure with the block. This is the processor. It's actually not a processor, it's a system on chip. The entire thing that you see in this block is present inside this chip. It has 4 cores, core 1, 2, 3, 4. An entire core is this blue box which contains an ARM 32-bit CPU, a Neon SIMD engine, a floating point unit. What is this floating point unit? Well, this is a unit that is used to do floating point operations. Why? Typically used in graphical processing units for doing image related algorithms. All image processing algorithms that you are going to run on, they need specialized hardware because the data that you work with in case of images are mainly floating point data. So you need sophisticated units. They are not integer operations. Okay. So floating point units that will handle the graphical data. Look at this block. This entire block, as you see as one, is one core. Similarly, you have 4 cores, right? 4 cores. And all these cores are sharing some memory. So they have a common memory that's also inside. Everything in total is one chip. And it's called Cortex A53. This is the family of ARM chip. This company is the most widely used and the most popular company for designing embedded chips. So chips that are used for these kind of low power computation. Okay, as you see, Raspberry Pi is a board which makes use of this chip for computing purpose. Some common IoT platforms that you will be working with. One of them is Arduino. That's again a very popular, very low cost computing platform. And this is the Arduino board that you see. There are different families. We're talking about a family called Uno that also has a microcontroller, but it does not have an so powerful core as ARM. It has a very simple Atmega microcontroller. It's a very low end microcontroller that is present in Arduino. So obviously Arduino has a very comparatively low powered microcontroller as Raspberry Pi. The programming, because the microcontroller is a very raw one, it has a microcontroller which is Atmega. So it does not support the high level processing, such as you don't have an operating system loaded into that. You neither have libraries, so it does not have all that. You have to code it in a very raw way, very similar to how we used to code 10 years ago the different microcontrollers. They have their own. Previously, we used to code microcontrollers using assembly. For example, if I coded 8051, I had to write in assembly. Then it was shifted, and then people thought that, okay, writing in assembly is difficult. Let's give a more easy way of coding. So they came up with this kind of interface where you could write codes very similar to C language. And this is the Arduino interface that you see. Look at the code that you see here. It's very, very similar to structures following C. You have void, which is for setting up the environment. You initialize, give a pin type, the mode, and then you write your logic here, which is again a very commonly used structure similar to C, where you have void, loop, and there you write something to this particular pin, put a delay, then you write and delay. So what you are trying to do is like read, write something. So this was given the interface of coding, and the platform in turn converted that into an executable and put that into the processor memory or the controller memory. And then the controller executed, the microcontroller executed. But as you see, it's a very low-end microcontroller, does not have a lot of processing power, a very low cost, and you have to write a limited amount of code because it only supports only some small amount of memory. So anything you would like to work with Arduino, good enough, but you have to use other devices as add-ons that only you can work with. So for example, it does not have a Bluetooth connection, it does not have a Wi-Fi connection. So you have to purchase Bluetooth modules, connect them to the Arduino board, and write a code for accessing those Bluetooth modules. Okay. On the contrary, this particular board, which is Raspberry Pi, which hosts this processor, it today has it has a more power. It's kind of a mini computer. And this processor, you can actually put a software, which is an operating system, into that. It has an onboard Bluetooth module. It has an onboard Wi-Fi module. So you need not have those connected as accessories. You can get it if you purchase the board. It's on board. And as you see here, this is the processor. It has a lot of accessories and peripherals provided for different data acquisition. For example, there's a display connector where you can connect it to the screen and visualize the display or visualize the output. You have an SD card slot. It's not shown, it's actually beneath. So you can have a micro SD card where you load your operating system, the Raspbian OS, which is a Linux. It's a Linux variant, and it supports Python. So you load that and you plug it in to boot or to load that software into the memory of this particular processor. You have a micro USB power that provides you the power. So it can simply be powered up through an USB port. 5-volt supply is good enough. You have an HDMI port for data interchange through multimedia data. You have a camera connector. You have connection for internet. It's a wired or LAN connection. You have a USB which you can connect your keyboard and mouse. You have status LEDs to give you an indication that whether the board is working correctly or not. You have audio jack through which you can get audio signals. You have data to capture video. And very, very important, you have GPIO headers. GPIO stands for General Purpose Input Output. They are general purpose input and output. So these are pins that are actually internally connected to this core. And you can take out these pins and you can use them for connecting to devices, external devices. I'll be showing you just now. So this is basically the common IoT platform. We'll be using this for our tutorial and lab. There are other computing platforms also available, and there are a number of projects that you see which is available on the internet using different kind of platforms. One very commonly used platform is Node MCU. It's also a very low cost computing platform. It has, as you see, lot of interfaces which are provided, also has a sufficiently strong microcontroller inside. And yeah, so there's some boards. There's a Beagle board. This is the embedded board provided by Intel. It's called Intel Edison. That's also used for typically for IoT purposes. It hosts Intel's own embedded chip for this purpose. We will be basically concentrating on the Raspberry Pi board. And now, now let's come to, so we understood the microcontrollers, we understood sensors. Now it's time to connect the two. The sensor will deliver the data to the microcontroller. Okay. Now for that, you need to have an interface. So the interface is very, very important. Primarily, there are two kinds of interfaces that are used. One is called the parallel type, which is a multi-line, many lines. So this interface, if it is a parallel, okay, it will have many lines here. And if it is a serial, right, then we'll have only one line. So multi-line and a 1-bit line if it is serial. Because it is parallel, it is able to transmit several bits simultaneously. And in serial, it's only one by one. But the problem is today, even if parallel is going to convert a lot of bits at the same time, they take a lot of space. So to reduce that, people go for serial, but you may wonder, well, that is sending 1 bit, so it's taking a lot of time. But high performing serial lines have been devised, and USB is one of them. It's universal serial bus. So you have serial interfaces that have been, modified, improved, and now they are high performing. They send the data single bit, but very fast. So there are a number of interfaces that have come up. One of them is called USB, that allows a person to connect an electronic device to microcontroller. We've already seen that. I won't go into the details of all this because it's available on the internet. Please go through that. The second one that we will be primarily be using in our tutorial and lab are these general purpose input output. What are they? Well, they are generic pins. Okay. As you see here, this is a Raspberry Pi, and this is the connector, which is the 40 pins that you see. And each pin is a generic pin which can be used as an input or an output. You have to tell whether you are going to use it as an input pin or output pin. So good thing is that the user can control at runtime, okay, depending on whether you will be connecting. For example, you want to connect a LED. So you will take maybe a switch, okay. So you can take one pin, connect it to the switch, and the other pin you can connect it to a bulb. So if it is switch, it's an input pin because that pin takes input from the switch. And if it is a bulb, it is an output pin. Okay. So in this way, you can, in your program, you can tell whether I will be treating GPIO1 as input or output. That's user controllable. That's the facility that is given. Then we have the third protocol is called I2c. I already have mentioned that. It's a very good protocol to connect a lot of devices to a single microcontroller. We call it a master and the others as a slave. So what happens is these are two lines which are data and clock, and they form a bus. So you can connect a lot of other devices like a sensor, a clock. So these are called slave devices. So once they get connected, the microcontroller has to identify the address of that and then send the data to it. And it goes through this data to the sensor, or it collects the data from the sensor to this. This is how it works. But there is a way in which the data has to be sent, and that is called this bit information. So there's a protocol. So the I2c protocol says that overall, this will have 1 bit, which will define the start bit. It will have 7 bits, Then there will be a read or write bit, whether you want to read it from the slave or write it. You want to have an acknowledgement because there's a handshake involved. You are sending it to the slave and getting whether you have received correctly is mentioned through something called acknowledgement. It's like if you receive a letter, I send you a note saying that, okay, I received the letter. Whenever two devices communicate, there's a handshake. Then there's a data frame that will actually contain the data. This is about address that data, because a lot of devices can be connected. So you have to identify the device that will require an address. So we have a start, we have the address of the slave, we have a read or write, what kind of operation you want to do, acknowledgement, then the data, then the acknowledgement, then again a data. So in this way, 16 bits, then an acknowledgement, and finally stop. So if I put it as like 1, 7, 8, 9, 10, 18, 19, 27, 28, and 29, something of this sort. So this is total, this entire bit will be one data that you're going to send from a master to a slave. So the data that you have obtained from one sample will be encoded into this particular form and then will be sent in or will be received from this. Okay. So this is the basic idea behind I2c protocol. The fourth protocol is called serial protocol, which also uses a master slave. And here we have same thing. We have a controller that initiates the start, gets the data, and then stops. There are two others. One is called the UART. As you see, it's not basically a protocol, but a connection. And this is what we also use very frequently. It's one of the ways by which you can convert a parallel data into a serial data. Here we have a data bus, which is, let's say, 8-bit. Parallelly, you send it to this 8-bit input. UART stands for receiver transmitter, universal asynchronous. If you want to communicate between two devices, you have to use an UART device on both sides. Let's say your sensor is using an UART. So your sensor will have this part and your microcontroller is receiving the data. So this will have this part. So the data that you capture, the 8-bit data, you will be sending it to this 8 lines of this UART. And via this TX line, that is transmit line, because it's a transmitter, it will be sending. It will send all these 8 bits one by one. Look at this. Okay, it will send this one by one. And who will receive that? The receive pin of the microcontroller. The receive pin of the, UART connected to the microcontroller. So it will receive that and then will translate this back into an 8-bit data. That's the beauty. You get 8-bit data, serialize, send it serially one by one to the receiver. At the receiver, you collect them, and 8 bits you collect one by one, and then you obtain it as an 8-bit data. This is, so for that you have two UART on two sides, one at the sensor side, the other at the microcontroller side. Often these modules are, present within the sensor node as well as in the microcontroller board. So you need not worry about that. If not, you have to purchase and connect them. The other 6th one is called RS-232, which is used for obtaining the communication. This is called a serial connector. Normally we don't have that now. Previously we used to have, it's a 9-pin connector where again the data is transferred serially one by one. Okay. It was previously used for connecting to printers. The CPU that we used to have, the desktops, the printers used to be, parallel port, and there are some ports were serial. Okay. So let me finish off this with an example which shows how we'll be connecting microcontrollers, and I'll be ending up that with this code. So let's see. Are you with me, all of you? So let's assume that we are using a sensor called Sonar range finder. What is this? It's a sensor that is able to detect an obstacle. What is the physical principle behind that? This is a sonar range finder where you have a transmitter and you have a receiver. Okay. So what happens is the transmitter generates some pulses at a particular frequency, 40 kilohertz, 8 pulses. And this pulse is sent. It's sent. If there is an object, this pulse hits the object and gets reflected. So this pulse gets reflected, and this reflected pulse is captured by the receiver. So this is the principle. It's basically kind of an transmit reflect mechanism. Transmitter reflects. If there's an object, it hits the object, reflects, and the receiver receives that. So if the receiver receives this pulse, we understand that there's an object. Okay. Now, how do you trigger this, that the transmitter should work? You send a triggering pulse. Okay. So once you send the triggering pulse, the transmitter becomes active and starts sending pulses. And when you receive an output pulse, you know that there is some reception. So these two lines are two lines called trigger and echo. So if you look at this sonar sensor, you have something called trigger, which is the pulse which will trigger the transmitter, and we'll receive it through echo. And then we have VCC and ground. This is overall the picture. This is the sensor chip. This is the circuit diagram as you see. Okay. Now, let us try to make use of this to code. What I want to do is I want to, write some code in the microcontroller so that the microcontroller can interface the data obtained from the sonar rangefinder. What I'm going to do, I will be set the trigger pin as output. Yes, because the trigger pin will be sending out pulses. So I will have to program this so that the trigger pin will be treated as output. I will be receiving through the echo pin. So the echo pin will be input. And I will be receiving the data. So I will be fix up a rate at which I will receive the data. Okay. This is my setup. And what is my loop? What is the execution that I will be doing? I will turn on the trigger pin 1. Look at this pulse. I will be triggering this 1. I will be applying some delay. I will wait for 10 microseconds depending on the frequency. Then I will make this 0. So I just sent out 1 pulse, and that is enough to trigger the to make the trigger. Then I will be reading the echo pin. I will read the echo pin and will record the duration. Okay, because if there's an obstacle, I will receive the echo. Then I will do this calculation. I will calculate distance by using this formula, the duration times 34300 by 2. Print the distance on the serial monitor. I have a serial monitor on which I will print it. This is the logic. Okay, so I'm using my Raspberry Pi. I'm connecting this sonar rangefinder with Raspberry Pi, and I'm programming my microcontroller so that it is able to trigger or get the data from the sonar rangefinder. So it's like interfacing my sensor to the Raspberry Pi so that I can collect the data. Let's see what I have done. I have made use of this GPIO extender. So I'm using some GPIO pins. By the way, this white thing that you see here, it's called breadboard. What is this breadboard? This is an connecting environment. These lines that you see here, okay, they have internal connections. So this vertical holes are internally connected, one column. So if you connect any wire to this hole, all holes will have the same connection. It means connecting to all the holes. Any wire connected to one hole of one column means connecting to all the rest of the holes. Not this one. These are two separate. These two are separate. And this is horizontally. Connecting a wire here means connecting to, by the way, all the holes in this same connection. Connecting a wire here means you are connecting to all the holes here. Okay, so this part is horizontal. This is vertical, but vertically only for one column. This is called breadboard. So I have fixed up my sonar here. So I got, because they are connected, so these 4 lines, 1, 2, 3, 4, these 4 lines have been connected to 4 holes here. I have connected them in this. So remember, they are not vertically connected. They are, I told that they are horizontally connected. Sorry, they're vertically connected in this. Here I have put them and connected it here. So these 4 lines to which they get connected is 1, 2, 3, and 4. These 4 lines are 4 separate lines because they are horizontal in this case. So they are separate. So I have to connect them, one to VCC, one to ground, and the other to echo and trigger. So what I do is I make use of these GPIO pins. And if you look, this GPIO pin is a voltage, 3.3 volt. I take a wire from here. I connect it to this. Because I connected it here, entire thing is connected. It's a horizontal connection up to this. And from here, I connect it to this line. And I told you that the entire vertical line is connected. So that means this line gets a 3.3 volt connection. I repeat, this is 3.3 volt. I take a wire, I connect it to this hole. This whole connection means this entire horizontal line up to this point. Anything you connect here is the same connection. Now you take a wire, connect it here. So this line, this hole and this hole gets connected now. And from here, connecting it to this hole means connecting the entire column. So the entire column gets connected. And what you have put in this column is this line, which is VCC. Same thing you use for the ground, right? You take one of the ground lines in this GPIO pin and connect it. Now you're left with 2, the echo and the trigger. Find out their pins. For example, this line, this blue. So what you see is this is connected from here. This is connected to this. I'll come to that. Let me just quickly go through this process. So the code basically is divided into 3 halves. One, this part, the setup. This is the function declaration. And this is the loop. Just remember the idea. Set the trigger, get the echo, compute the distance. This is the logic. What is this? Well, this is for setup. What have I done? I have used 2 statements. I think you have gone through some basic idea of Python. Let me just quickly go through. These 2 statements are for importing some class. Which class? RPI.GPIO. What is this? Think as a module that you are importing. What is this module? A collection of functions. What do they have? Some definitions of modules or some definitions of some functionalities that you can run for Raspberry Pi. If you want to use the GPIO pins, you have to include those libraries which is already defined. These libraries come pre-installed. When you install the OS Raspbian, they come pre-installed. So you don't have to worry about including them. You simply write this line import rpi.gpio. rpi.gpio is a library or a module, and you include that. If you include, now you can use them for different purposes. Then the next thing you do is you set up the pin numbers of this GPIO. There are 2 ways in which you can set up. One is called BCM, which means you are actually mentioning the pin numbers of the processor. And the other is the board. They are physical pins. So there are 2 ways in which you can mention the pin numbers. Either you can board pins or the processor pins. If you are using BCM, you are actually mentioning the Broadcom processor pins. So GPIO can be mentioned in terms. You have to first declare which mode are you going to follow. So I'm using GPIO.setMode. This is the library or the module name. This is the function that I'm making use of. SetMode is the function defined in GPIO library or RPI.GPIO library. And I'm mentioning as a parameter GPIO.BCM that I will be using the pin numbers of the board, of the processor. Then I am declaring the pin numbers. The trigger pin I will be calling as pin number 18, and the echo pin I will be using pin number 24. Okay. I am defining a function. Functions are defined in Python with a def sign, and then I will be using this. Then I am using two modules, which is like setting up my the two pins, trigger and echo. These two lines here, I'm using GPIO.setup and mentioning that the pin trigger, which I have defined here, is an output pin, and pin echo is an input pin, right? So basic two things you have to declare, import the libraries, set the mode, define the pin numbers, mention the ports as output or input, and now goes the execution. What? Well, you first make the trigger high by writing it to be making it true. GPIO.output pin trigger is true. This makes it. Then you wait for some time, put a delay. Then you make it false. That is, you bring it to 0. So here you used the trigger pin as high and then low. Then you measure the start time. You initiate a time. You initiate a clock to measure the start time and stop time. And then you apply a loop where you try to find out what is the value of the echo. Record the start time, record the end time, and calculate the distance. So this is the distance you have. So if you look at the entire code, you're actually following this. So what we did is we understood the interface of the sensor. What does the sensor have? It has trigger, echo, and has to be powered up by VCC and ground. So I will be using this trigger echo. I studied how can I initiate the trigger. I understood that the trigger has to be given a pulse. And how do I get the output? By reading the echo. After I get the echo, what I have to do? Well, I have to use a formula to get the distance. This is what is the basic idea of interfacing your sensor to Raspberry Pi. This is again an example of how devices are connected. Here we are showing a very simple device like a switch and an LED that is connected. So I'm importing again this library. I'm setting up that I will be using these pin numbers. I'm setting up the pin numbers here. I can directly use the setup where I'm mentioning that 25 pin and 18 pin will be treated as input and output. And then I'm using a function where I'm saying that I will be treating the pin as an input, and toggle, when I will be using this function toggle, what it will read is it will convert the state to its complement and will send it at the output. This is what toggle function will do. This is the execution. Here I see that if the input pin is a pin number 25, if pin number 25, which is an input pin, is true, that is, it is 1, I will call the toggle function and will pass the pin value, which is 25, to that. And what it will get is, the LED value, which is 18. And what it will do is it will toggle that, because here the definition of toggle says that it will change the state. So if the pin number 18 is at false, it will make it true. If it is true, it will make it false. I use a user-defined delay, and then I exit. So this is the idea of interfacing sensors to Raspberry Pi. So with this, I finish off our basic idea of hardware components in IoT. We covered sensors, we covered sensing circuit, we covered different kinds of sensor nodes, computation, actuators, microcontrollers, and interfacing sensors to microcontrollers. Okay. So